neutralization reactions and how we use those to do what's called titrations, which can help us determine the pH of a solution if we know the concentration of another solution. So I'm here to remind you of your strong acids and your strong bases. You should have these written down in your notes, and once again, you should be memorizing them. Okay? So, if we compare compounds, okay, as a reminder, ionic substances that are not bases, they completely dissociate. They have high conductivity, they're strong electrolytes. Covalent substances, okay, nonmetals plus nonmetals, they don't dissociate, they don't have conductivity, they're not called electrolytes. Strong acids and strong bases completely dissociate. That means they have high conductivity. They are also strong electrolytes. Whereas weak acids and weak bases, they partially dissociate, so they're going to have an equilibrium, which is a totally different unit that's going to be at the end of this semester. Their conductivity is low, so they still conduct a little bit of electricity, and we call them weak electrolytes because they weakly conduct electricity. So neutralization is what happens when an acid and a base react in a double replacement reaction to form a salt and water. Okay, so thinking back to first semester when we talked about double replacement reactions, and we said for it to go to completion, you either had to make an insoluble solid or water. Okay, so that's the case here. We're making water. We call any ionic compound that's a result of a neutralization reaction a salt. So it doesn't necessarily have to be sodium chloride. Okay, so acid plus a base results in a salt plus liquid water. So we're going to start by writing the balanced neutralization reaction. We're going to identify the acid, base, and salt in each reaction. So how we're going to do this, okay, I always, just like we did when I did double replacement, I'm going to circle my hydroxide and I'm going to circle my hydrogen. Okay, I know that those bond together to form H2O. Okay, and then we have potassium and chlorine here. Okay, as a reminder, potassium has a +1 charge and chloride has a -1 charge. So when they bond together, they're just going to be KCl. We have one of each. Okay? Now, this that formed, that's our salt. The thing that donated the hydrogen, okay? This HCl donated the hydrogen. That's the acid. Also, you should be able to identify that. That's hydrochloric acid. KOH, okay? That's one of your strong bases. So that's obviously a base. Okay? So same thing I'm doing here. Okay? I've got H, I've got OH, I've got H2O. Okay? And then we're going to have calcium. And then this is an acetate ion. So acetate, if you remember from your polyatomic ions, is a -1 charge. And calcium is a +2. So what we need to do to balance that out is have calcium bonded to two acetate ions because we want to make an uncharged compound. Okay? This is not quite balanced. I do need to make two waters. Okay? Calcium hydroxide. Okay? It's got hydroxide. That has to be a base. That has to be an acid. Okay? I'm going to give you time to figure out the last two. Okay? I'm going to give it about 30, well, let's say 20 seconds here. If you want, you can pause the video to give yourself more time to make sure you have these things correct, or you can work ahead. All right, go ahead and check your work. Let's make sure that you did this correctly. Hopefully you did. Okay, now we're going to talk through titrations. What titrations are a method used to determine an unknown concentration of a solution by using a known concentration of solution until the solution is neutralized. Important part of a titration is what's called the equivalence point, and that's the point in which the moles or the concentration of hydrogen ions is equal to the concentration of hydroxide ions, and that occurs at a different pH for different titrations. So what you'll see are these titration graphs, and a question that I may ask you is what the pH is at the equivalence point here. So what you want to look for to find that is the midpoint of this straight section. Okay, so that's about here, and if you carry that straight line over, so I'm going to actually, have a straight line. So estimating, that's about 8.5. Okay? And so that's the type of question that you might get on a quiz or a test. What's the pH at the equivalence point? And I would just give you a titration graph, and you would just need to figure that out from there. Pretty easy. Okay? Or I guess I said 9 here. Now, indicators. What indicator you use is pretty important. So if you're not using a pH meter to measure the exact point where the pH changes and that equivalence point, then we need to use an indicator that would change around where that equivalence point is. And that point at which the color changes is the equivalence point. Okay, we are going to be calculating where that happens, or quantifying where that happens, using this titration formula. Once again, not going to have you memorize it, you will always have this, but an important thing to note is that the coefficient for the base is going to be multiplied by the molarity of the acid and the volume of the acid used. And then the coefficient for the acid in the neutralization equation is going to be multiplied by the molarity of the base and the volume of the base. Okay? Now for volume, you can use milliliters or liters. It just has to match up between, like, you have to use the same unit for volume of acid and volume of base. That's the important distinction. So what we want to know is what is the molarity of a cesium hydroxide solution if 30 milliliters of the solution is neutralized by 26.4 milliliters of a 0.250 molar hydrobromic acid solution. So just like we always do, I want to write down the things that I know and the things that I do not know. So first of all, something that I know, I'm going to need to use this Ca Mb Vb equals Cb Ma Va, okay, equation. And then I'm also going to want to use a neutralization equation so I know what my coefficients are. Okay, so we have these two reacting. I'm going to assume it goes to completion. So we have water that forms, and then cesium bromide. Okay, and those actually end up forming, and it gets balanced, so our coefficients are 1, which makes things easier. Okay, this 30 milliliters, okay, that's the volume of our base, right? Because this OH tells us that's a base. So this 26.4, that's the volume of our acid. And this is the molarity of our acid. And what we're looking for is the molarity of our base. So now I'm just going to plug things in. So our coefficient that's in front of our acid is 1, so I'm not going to put that in there. The molarity of our base, we don't know it, so I'm going to just put MB because that's what I'm going to solve for. Volume of our base, we've got 30 milliliters. Okay, and then coefficient in front of our base is just 1. Molarity of our acid is 0.25, 0 molar, and then we have 26.4 milliliters for the volume of our acid. Okay, now I'm going to divide each side by 30 milliliters to get the molarity of our base by itself. So we should have 0.250 times 26.4 all over 30, and that should give us just molarity left over there because those milliliters are going to cancel out. So if we type that into our calculator and take into account some sig figs as well, our answer is going to be 25 times 26.4 divided by 30. Okay, we have 0.22, and each one of these had 3 sig figs, so I'm going to pop a 0 on there so I have 3 sig figs in my answer. So 0.22 molar is the concentration of the CSOH. Okay, so that's your answer. Let's move on to the next example. What is the molarity of a nitric acid solution if 43.33 milliliters of a 0.0 molar KOH solution is needed to neutralize 20 milliliters of this unknown nitric acid solution? So once again, I'm going to start labeling these things. Okay, so KOH, this is our base, nitric acid, that's our acid. So this is going to be the volume of our base, okay, molarity of our base, volume of our acid. Okay, we have KOH reacting with nitric acid. Now remember, HNO3 is nitric acid. Those are going to react to completion. We're going to make water and then potassium nitrate. Okay, that's nice. Those balance out equally, so we don't have to worry really about the coefficients. So we're going to have coefficient in front of the base times the molarity of the acid, which we don't know, Ma, times the volume of the acid, which is 20. That should be equal to the coefficient in front of the acid, which is 1, times the molarity of the base, which is 0.1, times the volume of the base, which is 43.33. Okay, I'm going to divide both sides by 20, and so what I have is 0.1 times, actually, let's erase that because it's easy enough to do that, 0.1 times 43.33 and not even type that into our calculator. So let's just put, that should be 4.333. We're going to divide that by 20. That should get us to molarity. So if, do this, okay, type that into your calculator, 4.333 divided by 20. Oh, that is the same answer as last time. Sorry, I got very confused. So I'm going to make it so we have the correct number of sig figs, which is 4. And that just happens to be the same molarity as the base from last time, which is why I was getting a little bit flustered there. But that works out amazingly nicely. Okay. Let's do another example. I think one last one. Nope. Okay, what is the concentration of a household ammonia cleaning solution if 49.90 milliliters of a 0.59 molar HCl hydrochloric acid, is required to neutralize 25 milliliters of the solution? So we have ammonia, which if you remember is NH3, plus HCl. Okay. That is going to neutralize, quit this, your neutralization reaction for that is going to end up being NH4Cl. So this is a little bit different. It's only going to form that salt because you don't have the hydroxide in there with it, which is fine. So what we have is the volume of our acid. We know the molarity of our acid. We know the volume of our base, and we need to find the molarity of our base. So base, acid. So what we have no, I actually want to do molarity of my base times the volume, which is 25. That should be equal to 49.9 times 0.59. So MB, if we carry that all out, we got 49.9 times 0.59 divided by 25. We have 1.18 molar, which should be equal to the concentration of our NH3, because once again, that's our base. Okay, that's it for the examples that I have. You should have some practice and then a key that's up front to help you check your practice. Make sure you ask questions if you have them. Thank you.